This Appendix B to the Radio Design 101 series is where we cover some of the background of how matching networks are done. But it's a lot more than that. The title's RF impedance conversions. And as you can see in the diagram, there's a resistor in series with a reactive element. That could be a capacitor or an inductor. And we can look at it in the form of a series connection, or when we're doing design and analysis and simulation and so forth, we can look at it as a parallel combination. Sometimes it is better to do it one way than the other. Provides more insight, makes calculations easier, and so forth. So that's what we're going to talk about today. Now, before we get into the details, let's talk about applications. Why do we care? What is this stuff good for? Well, the answer is a lot of things. Here's an example where we're using a vector network analyzer to measure the loading that an oscilloscope probe presents to a radio frequency circuit. And it's not what you think. The scope probe may be marked something like 10 megohms in parallel with 15 picofarads. But when we measured it, we got 48 ohms in series with minus J161. That's the reactive part. And VNA also converted that to about 9.6, 9.8 picofarads. This is a series readout. 48 ohms in series with minus J161, or 48 ohms in series with 9.8 picofarads. That's not the way this is marked, and it's not the way you may think about it when you're designing your circuit. So we're going to look at how we convert a series form, such as in this readout, to a parallel form that may be more useful for design and analysis. In design and analysis, this material also comes in incredibly valuable. For example, let's say we attach the oscilloscope probe to a node on this RF amplifier circuit. If the scope probe really was 10 megohms in parallel with 15 picofarads, then we'd be able to ignore the 10 megohms and just incorporate 15 picofarads into this tuned circuit, and we'd expect a little bit of frequency shift, but no real effect on the gain. That's not what we're going to see. Moreover, when we're designing a circuit like this is a cascode radio frequency amplifier, we have to worry about its input impedance because we build a matching network to convert that to something like 50 ohms. And in order to do that, we may run a simulation, and the simulation may read out in a series form, but for the matching network design, we would probably like that in a parallel form. And in this video, we're going to show how that's done. So that's where we're going in this video. We're going to see how this relatively simple concept and relatively simple equations can enable us to do things that we couldn't do otherwise. Now, I've placed this video as an appendix to the Radio Design 101 series. And I did that because it involves complex numbers. And that's something we kind of tried to avoid in Radio Design 101. In particular, the RF amplifier used there was a common base type. And that particular amplifier configuration type, which was covered in episode 3, has a largely real input impedance. It's not a complex input impedance. And I always felt bad about leaving this material out. So that's why it's an appendix now. However, there's a third series that we have that is ECE topics, and I finally did a video on complex numbers. So if you're rusty on complex numbers or you haven't really gotten into them, this might be something to look at. But let's go ahead and proceed here. Complex numbers are really misnamed. They're not all that complex. They're just two-dimensional numbers. And they're often written such as this: Z equals R plus JX. And R is the real or resistive part in the case of ECE stuff, and JX is the so-called imaginary part of the impedance. But get that word out of your mind. It has nothing to do with imaginary. It's just a second dimension. It's just a two-dimensional number. It has two parts to it. And as we discussed in the ECE topics video, we can put that in either a rectangular form or a polar form. And the polar form is perhaps a little better for understanding what Z is really doing. Z is an impedance. It acts kind of like a resistance, but it has an angle to it. So the voltages and the currents have amplitudes and phases, and we call them phasors. And the impedance relates the voltage to the current according to Ohm's law. These are not new expressions. This is just Ohm's law expressed in a couple of different forms, with the complex number Z taking place of the real number R for a simple resistor. So this slide attempts to capture most of the stuff we need to know going forward. The impedances could be composed of resistances, inductors, or capacitors, or a combination thereof. Typically we'll do two at a time, like resistors and inductors, or resistors and capacitors. So if you have a resistor in series with an inductor, then the total impedance is, not surprisingly, R plus J X of L, where X of L is 2 pi FL, as you probably know. On the right-hand side of this slide, we have some little bit more involved circuits. These are RLC circuits. They're resonant circuits that we use routinely in radio frequency design. And they come in two forms, either a series form or a parallel form. And their impedances can be expressed as shown. For a parallel circuit, the math can actually get a little messy, as we shall see going forward. But to simplify it and make it not as messy, we can write an expression this way. Z is equal to the resistance R in parallel with the capacitor's impedance minus Jx of C in parallel with the inductor's impedance, Jx of L. And in the Radio Design 101 series, we used these types of circuits a lot, but we concentrated on the reactances and the resistances, and we gave formulas like the one shown down here at the bottom. And in episode 3 of the series, those formulas were generally good enough to allow us to design this, for example, common base amplifier and implement the matching networks. But we avoided more involved amplifiers such as this cascode amp and its complex input impedance. And we talked a little bit about, but not too much about, the non-ideal characteristics of things like inductors and their effects on the overall gain. We treated the inductors, for the most part, as having the ideal impedance, Z equals Jx of L, where X of L is 2 pi FL. But real-world inductors are not ideal. Real-world inductors have some series resistance, and that's because they're made out of wire, but it's also because at radio frequencies, the currents that flow in the wire that makes up the inductor tend to only flow on the outside 1 micron of the conductor, and that makes the resistance go up. So the resistance can be quite high in a radio frequency inductor. In addition, the turns of wire are near each other and they present some capacitance, which in this simplified model is shown here. So anytime you're thinking about a real inductor that you're going to use in a radio frequency circuit, you probably should be thinking along these terms. Now, the capacitance can sometimes be ignored. It depends on what's called the self-resonant frequency of the inductor, which if it's much higher than the operating frequency you're using it at, you can almost ignore the capacitor. But the resistance in series with the inductance matters. And for a lot of circuits, like this one, the inductor is in parallel with a capacitor. It's forming a parallel RLC circuit. And so it unnecessarily complicates things if we put a series resistor right here. We'd much prefer if the inductor had a parallel resistance, because then we could combine it with, for example, R2. So that's what we're talking about here. We'd like to go from this model. We're going to ignore the capacitor. That's why I sort of lightened it up here. So just look at the R and the L. We'd like to go from this model to this model, from a series loss resistance to a parallel loss resistance. And oh, that's what this material is for. So, how do we do that? Well, if you're satisfied with the equations that I threw on the cover slide, then you can probably skip the next few slides here. But for a thorough treatment to understand what's really going on, I'm going to present the material. And it starts with a theorem. What's a theorem? It's a fancy math word for something you believe is true or is useful or whatever. Anyway, So the theorem is at a specific frequency an impedance, Z equals R plus JX, can be realized in either a series form or parallel form. The word realized means to make real, to implement it, for example. So if I have an impedance that I'd like to implement with resistors and capacitors, for example, I can do it either by combining a resistor in series with a capacitor or a resistor in parallel with a capacitor. Or, in the case of the inductor that we were talking about, a resistor in series with an inductance or a resistor in parallel with an inductance. Now, the theorem says we can do this at a specific frequency. And that's important because, in general, you may not be able to do this. In fact, you wouldn't be able to do this. Fortunately, for RF circuits, we're typically interested in operation at one frequency or a band of frequencies which is fairly narrow. So we can apply this at that narrow frequency. For example, the resonant frequency of a parallel resonant circuit. And to be clear, what we're saying is at that specific frequency, call it F0, the resonant frequency, these two realizations, you can create it one way or another way, but they are going to give equivalent behavior in the circuit that you stick it in. So you could build the circuit with this implementation, or you could build it with this one, and the circuit at that specific frequency will operate the same. So that's our theorem. Well, we need a proof. So here is a proof. I call this a constructive proof because it tells us not only that it's true, but also how to do it. Now, if you don't like slides with tons of messy math on them, well, I can sympathize with you. I don't either. But sometimes we have to do this. So I'm going to briefly go through it, and then I'll tell you you can freeze the slide and check my math if you want. But let's start off with the top here. It says the series form is trivial. Remember, we want to create an impedance R plus JX. Well, the series form, we just make RS here equal to the R that we want, and X sub S here equal to the X that we want. Well, that's trivial. I mean, that's straightforward. It's when we go to the parallel form that it gets pretty messy. So for a parallel resistor and reactance, or impedance JX sub P, by the way, the X here can be positive or negative. So if it's a capacitor, X could be algebraically a negative number. I'm just going to think of it as the inductor just to avoid that complexity, but if you work through the proof, it turns out to be true. So the parallel form is this. So what does that mean? Well, it means use the parallel resistor formula. I like to use the product over the sum of the two parts, and that's what this first term is. The next step is to multiply top and bottom by this stuff in parentheses here. So this is basically multiplying it by 1, so it's equal to this. But the reason we're multiplying it by RP minus JXP is so that the denominator will go to a real number, which is shown here. But the result is R plus JX is equal to this expression. But remember that R plus JX is RS plus JX. So we can look at this second two terms here as an equality, and we can match up RS with the first term and X sub S or JX sub S with the second term, which gives us these two expressions. So let's clean it up and solve for the RP and XP. What we do is we define a Q factor, RP over XP, and then we do some algebra. I'm going to freeze this here if you want and check it. But what it does is it gives us these two expressions down here. RP in the equivalent circuit, the parallel equivalent circuit, is 1 plus little q squared times RS. That's the thing to remember. And there is a companion equation to map from X sub S to X sub P. And it's shown here in one form. This is the form I used in class a lot, but I saw an interesting web page recently. I'll try to leave it in the comments below, that presented it in this form, which I think is a whole lot nicer. Now here's why this is nice. This is why this is cleaning it up. Because Q in general is going to be a number like 3 or 5 or 10. And so Q squared is going to be, generally speaking, a big number. So now we can understand what's going on. If you have an RS, a series form, and you want to convert it to a parallel form, when you do, the parallel resistance is going to be much bigger than the series resistance. Almost Q squared times that. But the parallel reactance is going to be actually quite close to the series reactance value, because this is 1 over big number, and so this is almost 0, so it's really XP is almost equal to X of S. And in the derivation, we defined Q up here as RP over XP, but it can also be shown that it's equal to XS over RS. That's the proof of this material on the cover slide, on the first slide. Okay, with that proof and those observations, let's turn to something much more interesting, applications. What can we do with this? We said in the beginning that a lot of test instruments will read out in a series form, and to understand what that means, it may be much more useful to have the parallel form, so this can allow us to convert. This is true of measurement equipment, but it's also true of simulators, as I'll show. This material is also used for deriving and understanding impedance matching networks, particularly the so-called L-type network, which forms the basis of many others, such as T-matching networks and pi-matching networks and so forth. We can also use this material to understand what are called parasitic behavior of inductors and capacitors, the non-ideal inductors, for example. And finally, how that impacts RF amplifiers and their design and performance. Let's start by looking at how to convert a series form impedance, such as read out on an instrument, to a parallel form that may be more useful in design. Here, we're measuring the impedance as seen looking into the tip of an oscilloscope probe. This is a vector network analyzer, and it was calibrated to this little BNC connector right here. That's where the reference plane is. The center pin of the oscilloscope probe is going into the center pin of this BNC connector, and the oscilloscope probe has one of these little RF spring clip things to contact ground. So I'm touching the ground, but I am not touching the center lead here. That's important. And you can see the probe is plugged into an Agilent scope up here, a fairly modern oscilloscope. Looking at the probe connector body, it says 10 megohms in parallel with 15 picofarads. Is it that? Well, I'm quite certain that's what it is at low frequencies, like at audio. But at radio frequencies, in particular 100 megahertz, where we're measuring, it's 48 minus J161 ohms. The 161 ohms, as we said before, translates to about 9.8 picofarads or so. But what is 48 minus J161? What does that translate to in a parallel form, such as shown on the scope probe? Well, let's see. Here's the calculation. And this is using these formulas that we had on the cover slide. So if we want to convert from a series form, RS and JXS, to a parallel form, we need this little thing called Q. And we can get that because we know XS and RS. So that calculates out to 3.35. Then it's a simple matter of plugging into the formulas. The RP value is going to be 1 plus 3.35 squared times the RS value, the 48 ohms. That works out to be 588 ohms. That is not 10 megohms. Now, this is at 100 megahertz. Again, at lower frequencies, it's going to be much higher. And ultimately, it'll be the 10 megohms that the scope probe is marked. You can see that on the Smith chart if you're comfortable reading Smith charts. At low frequencies, you go to this point, which we know on the Smith chart is essentially infinity, or something very, very high in ohms. What do our formulas tell us the XP value is? Well, we take X of S, which is 161 ohms, and we multiply by 1 plus 1 over Q squared. That works out to be 175 ohms. That's reactance. If we plug that into this formula to convert to a capacitance value, it comes out to be 9.1 picofarads. It's a little bit less than 15 pico, but it's in the ballpark. So that's okay. But this 588 will load a circuit, and if you're taking measurements, you may notice lower gain, wider bandwidth, and that's how I found this. I was measuring some circuits. I went, what's going on? Well, this is what's going on. So just remember this if you try to use an oscilloscope probe, even for a very high frequency. If it's a passive probe, then the oscilloscope probe can really load your circuit. Fortunately, there is a solution to this problem in the form of what are called active RF probes. This is an example from Keysight Technologies. We had a couple of these in our lab at the university. The loading was about 0.4 picofarads in parallel with 100 k ohms. The way they get that is they use an amplifier at the tip here that can then drive the 50 ohm cable, or whatever the impedance of the cable is, back to the oscilloscope, or spectrum analyzer, or network analyzer, or whatever you're using this with. The downside is these things are fairly expensive, although I found some on eBay. That's how I got them for the lab. So what else is this stuff good for? Well, coming back to our list, we can use it to derive and understand the impedance matching networks that we may use in an amplifier design like this. We can also use it to look at the effects of non-ideal components. Let's go there first, and then we'll come back to the matching network, because the matching network's a little bit more involved. So here's a cascode RF amplifier that was talked through in the Appendix A to the Radio Design 101 series. And this amplifier has a tuned circuit load that sets it at, say, 100 megahertz for the center frequency. And the gain is the transconductance of the transistor times the resistance seen looking out this collector up through R2 and then looking out through the load. So let's talk about the effects of L2 here. In reality, we know L2 is not an ideal inductor. So let's see what the effects are. First of all, assume we're at 100 megahertz, like I said. So that's where L2 resonates with C2 and this internal parasitic capacitance of the transistor Q2. And to be concrete, we'll assume that R2 is 3 k ohms. So this is 3 k ohms. And the transconductance GM is 20 milliamps per volt, 0.02 amps per volt. Then, if we have designed this matching network to convert whatever the load is, say 50 ohm load, up to 3 k ohms to match R2, because we think that's the output impedance, then RL prime here would be 3K as well. And we should have R, resistance seen by Q2, as that 3K in parallel with R2, which gives us 1.5K. And then a voltage gain of minus 30 volts per volt, or just 30 volts per volt in magnitude, which translates to about 30 dB. But that is all if L2 is ideal, and we know it's not. In the Radio Design 101 series, we talked about the quality factor of inductors, and it's somewhere between 10 and 100. I mean, it could be 5, it could be 200, but it's nominally in this range for most practical inductors. Depends on the size and how they're made. Now, if L2 in this design is a 100 nanohenry, then at 100 megahertz, its reactance is 63 ohms. And let's assume a really pitiful Q of 10. Now, this is not unusual. I mean, you may get this if you try to use a surface mount inductor here, at least a small surface mount inductor. If you get a large enough one, you could have a decent Q of like 50. I'll show you a case of that shortly. But let's assume that the Q of L2 is 10, then RS is 6.3 ohms. Where does that come from? Well, X of L is 63 ohms, so by the definition of Q, RS is 6.3, 1/10 of that. And then we can use our trusty formula. RP is 1 plus 10 squared, in this case, the Q squared, times the series resistance of 6.3, and that gives us 636 ohms. So, in addition to having L2 here, we have a 636 ohm resistor across it. So you have to think about that. It's not shown in the diagram, but when we're designing RF, we have to think about all these things. So that's here, and oh wait, that's in parallel with R2, which is in parallel with RL prime. And so the total R, as seen by transistor, falls to 447 ohms. It was 1.5K in the ideal case. Now it's 447. So the gain falls to 8.9, which is about 19 dB. So we've lost 10 dB. Not a good thing. So what do? Well, we get a better inductor. That's what we do. Now, we could also do this for the capacitor in the tuned circuit, but capacitors are generally much better than inductors. The inductors are the limiting factor typically. Okay, so we've talked about the loading of a probe that you put onto this node, for example. We've talked about how L2 degrades the LCR resonator if it's not a good high Q inductor. We haven't talked about matching network, although we did cover those in the Radio Design 101 series. But let's look at how the formulas we used there are actually derived. And how do we pick components to go in this box to actually implement that transformation from, say, a 50 ohm load up to 3K ohms? Well, here's the final result that I came up with for this particular case. I've got a 620 nanohenry inductor and a 4 picofarad capacitor. Notice the shape. It's sort of in an L shape if you turn your head 90 degrees. It's an L. So here's how we covered that at university. These are actually my handwritten notes that I used to make sure I said everything I wanted to say. So I'm going to go through these a little bit quickly just to give you a flavor for how the matching network formulas are derived. And then we'll look at this handout that shows you how to use it kind of in a cookbook fashion. But first, let's do the derivation. So here's what we already know from the series to parallel conversion formulas. They're given here. Q is XS over RS, then RP is 1 plus Q squared times RS, and so forth. By the way, these formulas for Q are easy to remember, especially if you've seen the Radio Design 101 series. You know that we have formulas for series and parallel RLC circuits, and the formulas are the same, really. There are some subtleties, and that's why I'm using a little q here, but we'll get into that maybe later. All right, let's take a simple example again of doing a series to parallel conversion. Let's say we have a 50 ohm load and we want to turn it into an impedance 50 plus J100. Well, that's easy. We just use the series realization and we add an inductor that gives us a J100 impedance, 100 ohms of reactance for the inductor. That works out to be 160 nanohenries at 100 megahertz. So what is the parallel equivalent of 50 plus J100? Well, we ran through the formulas here, and it comes out that the parallel resistance is 250 ohms, and the parallel reactance is 125 ohms. So the circuit that we get is right here. Now in this example, we started by saying, what if we want to create an impedance 50 plus J100? Well, we do that. But let's change it a little bit. What if we want to convert 50 ohms to 250 ohms? Can you look at this and think about how you might do that? So that's the next example, convert 50 ohms to 250 at 100 megahertz. So we kind of know how to get halfway there. We just add the J100 inductor, and then we view it in a parallel form. What do we do next? Well, we resonate out the parallel equivalent reactance. So we put a capacitor across this so that when we have a capacitor in parallel with the inductor, and they both have the same reactance magnitude, they basically look like an open circuit. And what we're left with is what we see down here. On the left is what we're actually building. We have a 50 ohm load and we put a series J100 and then we put a shunt or parallel minus J125. That looks like this. It's equivalent to this. And these resonate out and we're left with just 250 ohms. So this is how matching networks, L matching networks, are done. Okay, so that's L matching network design. Here's a summary of it on the right-hand side. I'll zoom in. The trickiest part is getting the orientation of this correct. You may recall that before the shunt or parallel was on the left, here it's on the right. Don't think left or right, think which side is it on relative to the higher impedance or the lower impedance. Remember, RP is always going to be higher, RS is always going to be lower. So the shunt side will be on the higher impedance of the two sides. And that's what these words are trying to say. The procedure is we compute the required Q value using the formula and a little algebra. And we can, if we know what RP and RS are, then, those are the impedances we want to convert from and to, we can solve for Q. And then we can compute the reactance as shown here. Now, note that there's a plus minus. That means that you can build these networks with say a series arm that's capacitive or with a series arm that's inductive. Whatever you do, the opposite arm, the shunt arm, has to be the opposite type. So if the series is a capacitor, then the shunt is an inductor and vice versa. And finally, we convert to the actual L and C values. And there's a note down here. If one component is selected to be capacitive, then the other is inductive. So we know that. The choice of which type to use for a particular side of the network depends on other circuit design considerations. For example, it will determine whether you get a low pass or high pass response outside the primary matching frequency. Now remember, these matching networks only work well around one particular frequency, which is okay because we're doing radio frequency design, which is typically narrowband. The choice may also affect the bias circuit design, and it may make it possible to save on the number of components in your final circuit. Let me show you an example of that. So here's the circuit we've been talking about, and we just implemented a matching network, and it is L3C3 in this particular schematic. Now this says C8, and up here it's C5. Just ignore that. This is auto-generated C values from LT Spice, so I didn't try to match them up. But anyway, this is a DC blocking cap that was up here. Are there any components in this circuit that we could kind of combine and reduce the part count? Well, I think I'll leave that as a problem for everybody to think about. And if you have some ideas, maybe put them in the comments. Don't read the comments ahead of time. Think through this. So look at this circuit and figure out what you might combine here. Being careful not to mess up the bias design in the process. While you're thinking about that, let me show you a simulation I did to check the final values that I got. So here's the computation of those values. The little q value needed to convert from 3K to 50 ohms turned out to be 7.68. And that gave us an X of S of 384 and an XP of 391, according to the formulas we worked out. And the C value then, if the series leg is a capacitor, is 4.15 picofarads. Well, you can't buy a 4.15 picofarad capacitor, so I just changed that to 4 pico. This is a schematic I'm using in the sim. And 622 nanohenries sounds way too exact, so I just changed it to 620 nanohenries for the sim. And hopefully, if we did this right, this L matching network will change our 50 ohms into 3K as seen looking in from the left side. So that's what we're showing up here on the schematic. Well, to check, I threw this circuit into LT Spice, which is a freely available software package that many people use. And I needed to figure out a way to ask it what the impedance is. And my favorite way to do that is to put an AC current source over here and across the two terminals that I'm interested in. And then run an AC analysis. So here I'm running an AC analysis in a linear sweep, 101 points from 80 megahertz to 120, because I'm interested in what happens around 100 megahertz. what's with the AC current source? Well, it's a little trick. If you set the AC current source value to 1 amp, now nothing's going to blow up here, it's just a simulator, so I can set it to 1 amp, and then I can look at the voltage that develops across these two terminals, because according to Ohm's law, V equals I times R, or in general, V equals I times Z. So I labeled this node Zn so I can just remind myself that I'm really, when I see the voltage, I'm getting the input impedance. And that's shown in the graph over here on the right. And the solid curve is the real part. And at 100 megahertz, follow this blue arrow line up and then come across, it's 3,000 volts. What does that mean? That means it's 3,000 ohms. Meanwhile, the dashed curve is the imaginary part, and if I follow it up at 100 megahertz or thereabouts, it's about 0. It's not exactly 0, but nothing is really exact at RF unless you carefully tune it after manufacture, which is quite expensive, so we usually don't do that. But this is close enough. The main point is the resistive part is about 3K ohms, like we wanted. You can also look at the bandwidth over what range of frequencies you're reasonably close to the values you want. All right, we have designed and verified the output section of this amplifier and talked about the non-idealities of things like this inductor. Let's now switch over to the input side of this amplifier and how do we design the matching network there. Well, if you watch Appendix A in this Radio Design 101 series, we go through this cascode amplifier design in great detail. And we talk about these parasitic capacitances, but also about the input resistance of this Q1 section of the amplifier. So the input impedance, Zi, looking in here to the base of Q1, is a capacitance to ground. This is a AC bypass to ground, so this node is AC ground. It's a capacitance to ground. It's actually, this is CBE, it's that plus 2 times CCB. This is CCB. But it's capacitance to AC ground. In parallel with a resistance, which is in general the R pi value of this transistor. So in parallel with, that means that the input impedance that we're after is essentially a parallel form when we look at the design process. But let's simulate it and see if those values are the ones that the simulator gives us for Zi. And here's how I did that. I put my AC 1 amp current source on that node. I'm looking through C5, but that's just a short circuit at our RF frequencies. So I can just put the current source over here. I did throw in a 1 times 10 to the 12th ohm resistor. That's to prevent what are called convergence problems in simulations, which sometimes occur if you have a current source driving into a capacitor. And so that's the purpose of that. It doesn't affect anything because it's 1 times 10 to the 12th ohms. So it's essentially an open circuit, but it does satisfy the simulation algorithm. Anyway, in our design process, we're thinking about the R pi in parallel with that capacitance, and we want to know Zn in this form. But guess what? The simulator is not going to give it to us in that form. It's going to give it to us in this form, a series form. And it says that the series resistance is about 65 ohms, and series reactance is about minus J360. So, at 100 megahertz, this is what the simulator tells us, but we want it in the parallel form, so we go through those formulas. And it works out to be 2.06K, basically 2K, in parallel with about 4.3 picofarads. Now, here's the thing. This is, however you look at it, a complex input impedance, and we didn't cover that, how to match to that, in the main Radio Design 101 series. We now know that we can view it as a series connection or a parallel connection of resistance and capacitance. And what we want to do is match up from 50 ohms to 2K in parallel with 4.3 picofarads. Now, we don't have matching network design equations and theory for matching to something that is a complex load. We assumed the load was resistive, but there's a trick that we can do to solve this little problem. Here's what we have. The input impedance is 2K in parallel with 4.3 picofarads. What if I ignore the 4.3 picofarads for a second and just design a matching network to go from 50 ohms up to 2K ohms? If I do that, then I come up with something like this, except that the capacitor value needed is about 4.9 picofarads. But look, I've already got most of that just in the input impedance looking into this part of the circuitry. So I got 4.3 picofarads. What would I need? I guess 0.6 picofarads. Here I use 0.4. I think that was because I did a little tuning right at the end. But anyway, 0.6, 0.4, 0.5, whatever here. And that would be enough. Actually, sometimes you'll see designs like this where it's so close that they'll just omit this. And they'll just have an inductor driving into the complex load. And I could check this by putting my current source here and making sure I get 50 ohms. I skipped that step because I was pretty confident. And I just put a 50 ohm source over here and looked at the overall gain. And here's what I got. The overall gain is about 26 dB. Now that is with my imperfect inductor. I did assume in my inductor that I have a Q of about 50. 53 exactly. I put 1.2 ohms here. And whenever you're doing this stuff, actually put a real inductor model in. Don't put an ideal inductor. Put the real stuff in so that your simulation gives you something closer to reality. And my gain looks pretty good. It looks about 100 megahertz. The phase is 180 degrees for the transfer function from the source to the output load over here. And that's expected because it's an inverting amplifier. So this looks pretty good. I was expecting higher gain though. But that's because my initial formulas weren't taking into account the degradation from this inductor. A couple final points on this. Notice that the source I'm using here says AC2. So it's a 2 volt input. And I'm looking at the output voltage and calling that my gain. Is that cheating? Why am I using 2 here instead of 1? Well, it's a subtle issue, but it deals with the fact that what we're really after is what's called insertion gain. And insertion gain is how much bigger is the output than it would be if the input was, if you were just driving into the input and you looked at the input with the 50 ohm loading it. So remember, there's 50 ohms standing here looking to the right. I got a 50 ohm source. And if I was just looking at the voltage I would get at this point, it would be 1/2 of this. So that's why this is 2. 1/2 because I'd have 50 ohms and 50 ohms to ground voltage divider. So my overall insertion gain is 26 dB here. There's a note at the bottom. We should probably delete R2 here. Why? Well, I'll let you think through that. Would that mess up the bias in any way? Always check that. But why am I saying maybe delete R2? And leave some ideas in the comments section maybe. So that brings us to the end of our list of applications and pretty close to the end of this video. Except for these couple slides that talk about what you could do to get more information on this. Aside from looking at textbooks and other YouTube videos out there, we have these 3 series. There's actually 4 series. There's one on antennas and propagation as well. So you might check out some of those videos if you haven't already. And there is an associated website with the URL is shown right here. And in that website, you can find all the slides as well as the presentations videos. Basically, that's links to YouTube playlists. But there's also some information on RF test equipment, prototype boards, if you want to do some RF prototyping, and all the university course materials that I put together when I was teaching this material. And you can see those over here. Caution, they are the handwritten ones. They're not real pretty slides, but the information is there. Okay, well, thank you for watching. If you got this far, I hope you did. And I hope this was valuable to you. So thanks again.